All right, in this video lesson we will be looking at mirrors and lenses and how to determine where images go and what size they are using both ray diagrams and the mirror and lens equation. So there are multiple types of mirrors. First we're going to start off with this one of the more common types of mirrors, which is a plane mirror, otherwise known as a flat mirror. With plane mirrors, they always make what are called virtual images, where the image looks like it comes from behind the mirror and seems to come from behind the mirror in the way it behaves. But of course, we know there's not actually anything behind the mirror, and the light never actually does come together there either. The way you locate an image with a ray diagram is you pick two rays of light, any two rays of light you want. Now with the other shaped mirrors, we'll see that it actually matters, like it makes it easier if you choose a certain two rays of light, but for a plane mirror it doesn't really matter. One coming in perpendicular to the mirror is oftentimes the easiest, okay, and then the other one is just whatever, however you want. So anything that comes in straight perpendicular to a plane mirror is just going to bounce straight back. And then otherwise, you know, because the angle of incidence equals the angle of reflection, if this one came in that way, it'll leave like that. Now, these two rays of light will never really intersect each other in front of the mirror. So what we do is we look at, well, if we trace them back behind the mirror, where would they intersect? So if we go straight back in the direction where they came, they intersect there. So this is a virtual intersection. It doesn't actually happen, okay? You can do the same thing with the bottom of your object. If it goes straight in, goes straight back. If it comes in at an angle, goes out at the same angle. They don't really intersect, but I can trace them back. And so again, there's another virtual intersection. And if you look at any place on the object, you will find that there's a virtual intersection of corresponding behind the mirror. And so we end up with a virtual image. With a plane mirror, that virtual image is always the same size as the object. It's always the same distance from the mirror. So if this was 1 meter, this would appear like it was 1 meter back, and so on. Mirrors can be curved, and so with a concave mirror, and a concave mirror is bent inwards. So we have the reflective surface on this side is the reflective surface. It says up here. So that's the reflective surface. Okay, that's for a concave mirror. With a concave mirror, because they're shaped, they still obey the law of reflection, but with a curve, it's a little bit harder to see that they do. But if you were to measure the normal, so like on this surface right here, the normal would be this way. And so anything that comes in, whoops, if it come in at an angle, it's going to bounce off at the same angle. Okay. Now, with curved mirrors, we always check two different rays of light. Any ray of light that comes in parallel to what's called the principal axis will leave through the focus, and any ray of light that comes in through the focus will leave parallel. So if I have a ray of light that came from here and it went from the focus, it will go straight back out. I can use that fact to locate the image of an object that's in a mirror. And I think maybe we'll just leave that and work a few of those together in class tomorrow. Okay? Sometimes if you want to be more precise rather than relying on your ability to draw things nice and precisely and following the rules about how things reflect off of surfaces, it's nice to be able to use an equation. Okay? And so these mirror and lens equations tell us can relate how far the image is from the mirror compared to how far the object was, when we know what the focus of the mirror is at. And it can also tell us how much the image is magnified. So this is the distance to the image. DO is the distance to the object. And this F is the focal length. And the focal length for a spherical mirror, as you can see back in this, the focal length is always halfway to the center of curvature for a spherical mirror. If it's a parabolic mirror, then it's a different relationship, or elliptical, based on what you've learned about parabolas and ellipses in math class. And then this other term here, M, stands for magnification. So that's how many times bigger or smaller the object is. If M is larger than 1, it's magnified. If it's smaller than 1, it's minified, I guess you could say. If the sign is negative, it means the image is both inverted and real. So it means that the image has been flipped. For convex mirrors, basically the same thing. They have all the same parts. They have a center of curvature. They got a focal length halfway. Now for here, since light's coming in this way, if light's coming in like this, it's still coming in parallel to this principal axis here, and it's still going to bounce off in the direction of the focus. So it's going to bounce off like that for light. And any light that comes in the direction of the focus is going to bounce off parallel still. Okay, they still have the same kind of geometry at work, so the rules are the same. When you put you work with convex mirrors in the mirror and lens equation, you always have to consider the focus to be a negative number because it is behind the mirror instead of in front of the mirror. When working with lenses, we also have convex and concave lenses. As you can see in the image here, a convex lens is able to focus light, which means any light that comes in parallel to the lens will leave through the focus on the other side, and any light that comes from the focus on this side will leave parallel. This again in the mirror and lens equation, these focuses, it is a positive focus that you have for these lenses. For a concave lens, they are divergent. So as you can see in the image, light rays that come in parallel end up being spread out. And this one actually has it drawn in for me, that now when the light comes in, comes in parallel, it leaves in the direction of the focus that's behind where it is. So since the focus is behind, concave lenses have negative focuses. So basically any optical device that can focus light or converge the light has a positive focus, and any lens that diverges light has a negative focus. This is a table here just to kind of sum up all the different types of images and images in terms of where they could be, where the object is located, what type of image we have, and if the magnification makes it larger or smaller. So with a plane mirror, and actually the same thing with a plane sheet of glass, no matter where the object is, the image that you form will always be virtual, and there will be no magnification. As soon as you start bending them, so if it's a convex mirror or a concave lens, no matter where you put those, they will again always make a virtual image that is smaller in magnification. When you have a concave mirror, convex lens, and again maybe I should point out that these are both diverging optically, and these are both converging. So when you have a concave mirror or a convex lens, when you're inside the focus, so you're close, it makes a virtual image, so that's where you have your magnifying glass. If you're outside the focus, you make a real image, and the size of that depends on where you are with respect to the focus. If you're anything larger than twice the focal length, it's going to be smaller. If you're anything closer to twice the focal length, it's going to be larger. Okay? So again, went through this kind of quickly. I want to be able to show you the ray diagrams kind of more in person to do a couple examples in class. The mirror and lens equation isn't too hard to do as long as you're being careful with your algebra.